Hello, everybody. Welcome to our RAG Hack live streams.
RAG Hack is a free global hackathon happening from September 3rd to 16th. RAG is a technique to get a large language model to answer questions based off your data. We have more than 25 live streams teaching you how to build RAG apps with different Microsoft technologies, plus 10 cash prizes for the best RAG apps in each category. So we're super excited to have you join us for this RAG Hack. And now a word from our friends at Reactor.
Hi, everyone. Thanks for joining us for the next session of our RAG Hack. My name is Anna. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenter to answer live. Our session is being recorded. It will be available to view on demand right here on the Reactor YouTube channel. With that, I'd love to turn it over to our presenter. James, thank you so much for joining us today.
Hey, I'm super happy to be here today. Hi, everyone. I'm James Codella. I'm a product manager in Azure Cosmos DB. I'm really excited to be here today to talk with you about RAG and Cosmos DB and all our great vector search and AI capabilities that we're continuing to build out into the database. So we have a lot to talk about and a cool demo at the end. So let's get started. So we'll go through just a quick primer of what is Azure Cosmos DB. We'll talk a little bit about some customers that are using it today for the real world generative AI applications, including for RAG and chat history and other scenarios like that. We'll talk a little bit about generative AI use cases with Azure Cosmos DB. And then we'll briefly touch on some of the really cool vector search capabilities that we've built and recently launched in preview for Cosmos DB, talk a little bit about what's coming up next, and then we'll dive right into a demo. We'll spend a lot of time there. We have a great Jupyter notebook where we're walking through a RAG example in Python using Azure Cosmos DB and Azure OpenAI service. So let's get right into it. So you may already be familiar with Azure Cosmos DB, right? It's the world's most scalable database for transactional operational data. I want you to think about Cosmos DB as the most scalable AI database now, right? There's so many AI applications being developed with Azure Cosmos DB because of the core value propositions and capabilities that Cosmos DB has built into its cloud-native scale-out architecture. The first is Cosmos DB is offered in a serverless or provision throughput model, right? So in serverless, you pay for compute, and you just pay for what you use. And in provision throughput, you pay for compute, but you pay for a certain amount of throughput that you're expecting for reads or writes or queries or vector searches or other sort of transactional operations on the database itself. Cosmos DB features automatic sharding and partitioning. You don't need to worry about how you're managing your partition strategy or your sharding as your database grows in size and as your applications scale, right? We handle all of that for you automatically. You just tell us some basic information about partitioning using what's called a partition key in the document itself. Cosmos DB is also known for its high elasticity with instant auto scale. So when you have periods of very high demand, Cosmos DB can scale seamlessly and instantly to accommodate the high traffic of inserts, deletions, queries, all sorts of operations that you would expect from a high-speed transactional database. Cosmos DB can do this at any scale and scale up for you when you need it and scale back in for you when the traffic subsides. Cosmos DB is also quite famous for its low latency real-time data transactions. We have an SLA of under 10 milliseconds for point reads and point writes in the database if your application is in the same region that you have your database provisioned. That's world-class speed and low latency for these sorts of central operations for a transactional database. We have mission-critical reliability, over 5 nines of availability in high availability scenarios. And Cosmos DB also has multi-tenancy built into the database structure itself. Whether or not you're isolating your tenants from a logical partitioning level to a document level to a collection level, database level, or even a resource level, there is a tenancy or multi-tenancy option for any one of your requirements using Cosmos DB for your multi-tenant applications. Finally, last May, we launched built-in vector indexing and search into Azure Cosmos DB, and we're really excited. So this is available in preview today. And it also features a vector indexing algorithm called DiskANN, which allows you to do fast and efficient vector search at any scale. DiskANN was developed at Microsoft Research, and we use it a lot internally at Microsoft. So for the first time in an Azure database product, we're making it available for you to use for your own vector search operations. And we'll talk about that a little bit more in a minute. So let's start at a high level. AI scenarios with Azure Cosmos DB for NoSQL. There's a lot of different scenarios that you can power using Azure Cosmos DB. We're going to touch on these top 3 a little bit here in our talk today. But there's even a lot more that we can talk about as well. Let's start with chat history, right? We have thousands of customers today storing their chat history from chatbots, large and small language models, and everything in between in Cosmos DB. And they do this so they can have conversational awareness with their large language models or their chatbots, recalling information when they need it. They also do this for later analysis, for improving their scenarios and making sure that their chatbot's doing the right thing. We'll talk a lot today and show a great example of retrieval augmented generation, or RAG. And today, we have lots of customers doing this with Azure Cosmos DB, powered by the built-in vector indexing and vector search capabilities that we have. Multi-tenant applications are huge for Cosmos DB. We have many ISVs developing their applications for many of their customers in Cosmos DB and keeping their data safe, isolated, and secure in the database itself. And there's really a huge growing interest in multi-tenant AI applications. We also have customers like ASOS.com building real-time recommender systems and storing those predictions in Cosmos DB and taking advantage of our low latency point reads to read those predictions at the time of inference when it's really crucial, say like if you're making a recommendation when the website's loading. We have customers like MasterCard who are leveraging Azure Cosmos DB as the data store for the real-time anomaly detection systems. And finally, we have many customers now exploring multi-agent AI. You have multiple AI models or AI agents working together harmoniously in order to achieve very complex tasks. And those interactions or communications between the AI agents are stored in Cosmos DB, so customers know or can investigate on how to improve the performance of their AI systems, or identify bottlenecks, or retrain models using some of the data that's stored there. So lots and lots of great use cases across a slew of companies of all sorts of sizes are using Cosmos DB today to power their AI applications. Let's take KPMG, for example. KPMG Australia has developed a chatbot called KimChat. KimChat's used to streamline some employee operational tasks and help them be more productive. They went from using a full text search for retrieval of information for their RAG scenarios for their chatbot. And they noticed that they weren't quite getting the performance or the accuracy that they were looking for. They switched to using vector search in Azure Cosmos DB, and they saw a huge jump in the relevancy metrics that they used to determine how relevant the responses are from their chatbot. They went from 50% to over 90%. They noticed real-world performance and productivity gains for their employees. And thanks to Cosmos DB's scalability, they're able to roll out KimChat to more and more KPMG member firms, so that way their own employees can take advantage of the great capabilities and productivity gains that KimChat has to offer. Next, we'll talk a little bit about OpenAI, right? So everyone's used ChatGPT. It's incredibly impressive. It's a great, fantastic service, and it's powered under the hood using Azure Cosmos DB as its chat history store, right? So when you have a conversation with ChatGPT, this is stored in Cosmos DB for later retrieval, for analysis. And OpenAI chose Cosmos DB because of our ability to scale seamlessly and effectively and handle the crazy amounts of traffic due to the popularity of ChatGPT in all sorts of scenarios and all sorts of ecosystems across the world, right? Cosmos DB is a globally distributed database, so you can expect, as your data is globally distributed, you can expect the same performance or the same experience for your customers, whether they're in New York, or whether they're in Tokyo, or whether they're in France. Really a great use case here for chat history to power one of the world's most famous generative AI applications, ChatGPT. All right, so we learned a little bit about Cosmos DB, and we talked a little bit about some of the customers who are using Cosmos DB for their AI scenarios. Now let's talk about what we're doing today with AI, or to power AI applications in Cosmos DB. So there's a lot of generative AI use cases that we can dive into, and the demo that we'll see in a little bit touches on all of these, right? The first is a vector and operational database together in one place, right? So as I mentioned, you can now store your vectors in Azure Cosmos DB, right? So Cosmos DB is a non-relational or NoSQL database. You can think of the data items stored as JSON documents, right? And a vector is just a list or an array of numbers, right? Floating point numbers that you can store as just another property of a JSON document. And so this is really powerful, right? I can store my vector embeddings and my original metadata in one place, in one data item, without the need to set up a different vector database just to handle my vector search operations, right? So I can keep my vector data and my operational data together in one place, remove the need to ETL my data to a vector database. I can make sure that my data remains consistent all in one place. And it also reduces the complexity and cost of my AI application infrastructure. On top of that, we have many customers building retrieval augmented generation scenarios. And again, you've all seen sort of the primer videos and a lot of the great content that's been part of RAG so far. So I won't rehash what's already been said. But it's, retrieval augmented generation is really about bringing the right data at the right time to your models, so that way you can personalize them for your scenario. And then chat history, right? So I talked about how ChatGPT leverages Azure Cosmos DB as its chat history store. And we have many customers doing this today to maintain conversational context, right? These small language models and these large language models are stateless. So if I tell a GPT style model, hey, my name is James, and then I ask it a question, what was my name? It has no idea what my name is, right? It doesn't have any sort of memory to sustain itself from one state to the next. So what I need to do is I need to actually send conversational history to give context and ground the model, so that way it remembers things that were talked about in the past. So this chat history data in storing Cosmos DB and taking advantage of our low latency, high transactional throughput models. But you can also use chat history for lots of different applications, right? I can use it to assess where do I need to make improvements in my large language model or in my user experience. Like where are my customers, where are my users struggling? Where is the model struggling? Or maybe do we need some prompt engineering or some few shot examples or fine tuning to improve the model? And then, if anybody who's called a customer support phone number and has talked to a customer support agent, you may have heard them tell you ahead of time that this call may be monitored or recorded for quality purposes, right? So we're already recording conversations between humans and humans. It's probably a good idea to record conversations between humans and AI agents or large language models as well. And we see this as very important for auditing purposes, especially in highly regulated domains like financial industry or healthcare industry. So really a lot of great use cases for maintaining chat history. And you can do this very securely and in isolation in Cosmos DB today. Finally, there's a notion of what's called semantic caching. And this has become very popular with a lot of our customers using Cosmos DB today. So the idea is, if I'm already recording chat history in Cosmos DB, say I have a question posed by a user, and then I have the response generated by my large language model. Well, what I could do is maybe I can use the large language model's response that it's made in the past and use this to answer similar questions in the future, right? So the idea is you take the user prompt or the user question, and you can create a vector embedding of that user question and store it in Cosmos DB. Next, in your chat application, if a user asks a question, rather than first posing it to the large language model and making a call to your large language model API, which could be costly in terms of money, but also costly in terms of latency, because oftentimes it's the highest latency operation that you'll do in your generative AI application. Instead, you can actually take that user question, create a vector embedding, and then do a very fast and cost-effective vector search in Cosmos DB. And if you find a relevant question that's been asked before, you can simply take one of the logged pieces of information from Cosmos DB and bring that back into your chat application. So this saves you time because it reduces latency for all the calls that you have, but it can also save you money, right? And saves on token consumption, because oftentimes calling a large language model could be one of the more expensive parts of your application pipeline. So lots and lots of interest in semantic caching. Some really great articles in the Azure documentation, Cosmos DB, for how you can go about implementing that. So, all right, so what can you do in Cosmos DB? So I've talked about vector indexing and vector search. Let's dig into that a little bit more, right? So last May, we announced native vector indexing and search in public preview in Cosmos DB. And what I mean by native, right? This is vector indexing and search that's built into the core database engine itself. It's not another service you have to deploy. It's not a node or a VM that you have to host and manage separately. It's part of the self-hosted, self-managed service of Cosmos DB. And you can execute vector searches just as another query that you would in Cosmos DB using your NoSQL query language. So it makes it really easy to use. Next, we announced the gated preview of DiskANN. So DiskANN is a state-of-the-art vector indexing algorithm that was developed at Microsoft Research. And that, as I mentioned, we're bringing to you for the first time in a Microsoft product for you to use for your vector search applications. And we also launched a few integrations with some of your favorite large language model orchestration packages like Semantic Kernel and LangChain. And through the course of the summer, we're continuing to make advancements on DiskANN optimizations, on reducing costs, on reducing latency. We're also expanding our integrations out. So we now have integrations in LangChain for JavaScript. We have integrations coming soon for Llama Index. And stay tuned, we have even more integrations that are coming out on the pipeline. So lots of really exciting stuff that we're launching and that we're continuing to launch in Azure Cosmos DB. So for vector search in particular, right? So we talked about how you get to store your data and your vectors together in one database, in one collection, even in one data item. So this reduces the complexity and cost of your generative AI applications. Next, because vector search in Cosmos DB is just another query function, you can actually use it in any Cosmos DB query, right? So if I have where clauses for range comparisons or inequalities or string matching or even geospatial filters, I can use all of the great functionality of Cosmos DB's query filters in conjunction with vector search to create very powerful and targeted vector search queries. So lots and lots of goodness that you get there. And then finally, we have flexible indexing options. So as you may recall, in vector search, there's usually a trade-off between latency or throughput, so how fast you can execute vector searches or what the latency is of returning a vector search. And there's a trade-off between that and the accuracy that you get, right? So you can do a KNN-based search, K nearest neighbor. So you do an exact search, sometimes called a brute force search. You have a query vector, and you compare it against every single vector in your database. And that gives you, 100% guarantee that you'll find the closest vectors in your database to your query vector, right? I'm going to scan every single vector in the database, compare it with this query vector. The problem with that is once your data set grows to some appreciable amount for a scenario, it becomes very computationally expensive, and it actually takes quite a long time to do these comparisons, right? And it scales linearly with the amount of vectors that you have. So most vector databases rely on a proximate nearest neighbors method, and you may have heard of some types like IPF or HNSW. And so in Cosmos DB, we offer DiskANN, which is a hybrid in-memory and disk-based vector indexing algorithm that we'll talk about a little bit more in a minute. So you can do a brute force search using the flat index if you'd like. We also have this quantized flat index, which compresses the vectors a little bit before you do a brute force search. And this could lead to even faster performance for a brute force search, which may be useful in a lot of scenarios. And then finally, for anything of appreciable size, anything more than a few tens of thousands of vectors, you can try out our DiskANN-based index, which gives you very cost-effective search at scale. And of course, all of these great vector search capabilities are built on top of everything that you get in Cosmos DB that makes it amazing, right? Serverless or provision throughput model, all our multi-tenancy options, the dynamic and instant auto scale, the low latency point reads and point writes, our global replication, and finally our industry-leading 5 nines of availability that you won't find anywhere else. Okay, so I keep talking about DiskANN. I'm really excited about it. Let's talk about a little bit about how it works, right? So most vector indices today build some data structure to make it very efficient to search for your vectors in the database. HNSW is a graph-based vector index that's stored in memory, and that makes it fast for in-memory operations, but it also makes it quite expensive when you're doing anything at very large scale. This is because compute and in-memory cost, or RAM cost, is actually much more expensive than, say, using a very high-speed, efficient SSD, right? And so DiskANN sort of takes the best of both worlds. So it starts off taking the core vectors that you insert into the database, and it takes them and it compresses them. And these compressed vectors are compressed through a method called quantization. In particular, today we use product quantization in Cosmos DB. But these quantized or compressed vectors are stored in RAM for easy and quick access. Now, the uncompressed vectors and the full fidelity graph data structure that gets created by DiskANN is stored on high-speed SSDs. And the search algorithm helps optimize the interactions between the vectors that are stored in memory and the full fidelity graph that's stored on high-speed SSDs. And the way that the graph is constructed is in a way to really reduce the search time, or the time that's spent searching the graph for the vectors that you're looking for. So the combination of these make it very, very powerful. So DiskANN allows you to do vector search very cost effectively, because it's using the SSD in addition to RAM. It's also very fast. It's using high-speed SSDs and RAM to actually help achieve low latency. And then also at scale, right? DiskANN has been used extensively in Microsoft at scale. Bing uses DiskANN in their own implementation where they do vector search on hundreds of billions of vectors at incredibly low latency. And so you're able to do things very cost effectively at scale. And the great part too is DiskANN is actually quite robust to data changes. So as you do a lot of insertions or deletions or these sort of operational transactions that Cosmos DB is really good at, the quality of the search, the quality of the results that you get back actually still remains high without having to rebuild the entire index. So all in all, this makes DiskANN very efficient and very good at scaling to large volumes, but also at these sorts of transactional operations that you come to expect from a world-class database like Cosmos DB. Okay, so we've talked a lot about vector search, about Cosmos DB, about DiskANN. Let's jump into a demo here. So what I'm going to do is I'm going to go through this demo. I'm going to use Jupyter Notebooks. I'm going to use Python. I'm going to use the Cosmos DB for NoSQL Python SDK. I'm going to use the OpenAI SDK to talk to some Azure OpenAI resources. And we're going to build a chatbot. And this chatbot's going to do a bunch of stuff. We're going to do vector search using RAG. We're going to store chat history in Cosmos DB as well. And then we're also going to show an example of semantic caching that I was talking about. So leveraging this cached or chat history data that was vectorized. So that way I can answer similar questions again very quickly and very cost effectively. So let's get right to it. All right, so I'll switch over from my slides to Visual Studio Code here. All right. So before I jump right into this, I actually have a little example notebook here. And by the way, there's a link to these notebooks at the end of this presentation and the slides. So you'll have access to all of these. They're up on GitHub, so you can go play around with this as well. But first, I'm just going to show you a quick example of executing a vector search in Cosmos DB using our Cosmos DB Python SDK, which is really powerful and really easy to use. So in this notebook, I just have some preliminaries, right? So I've set up, I'm just doing all my pip installs for any packages I want to use. I'm importing my libraries here. And then I have an environment file, which you can customize. And it just has all the connection details for Cosmos DB, the endpoints, the keys, same thing for Azure OpenAI, and some of the configuration settings. So we'll connect to those. We'll set up our Cosmos DB client connection, and we'll set up our connection to our Azure OpenAI resource that we have deployed. And then I have different collections of different sizes here. So I've gone ahead and I've actually made collections in Cosmos DB that have different size like a whole bunch of different documents with vector embeddings, right? So I've created a collection here that has 10,000 documents, or 10,000 vectors, 100,000 vectors. And I have actually a comparison between two different ways. So I've used a quantized flat index. So remember I talked about you can do a brute force or a flat vector search, and you can also do it using quantization, so a compressed method to do it a little bit faster. But I also have a instance here provisioned with DiskANN index, right? So I have a 10,000 and 100,000 size collection or container here. So I'll go ahead and just get those for my Cosmos DB instance. I've already inserted all the data, so I'm not going to bore you with the details there. But it makes it really nice for us to do a little comparison later on the different sizes and the different index types, and so we can see what the performance looks like. Okay, so now I have a helper function. And again, this is just calling my Azure OpenAI embeddings deployment model, right? This is just a little Python function that I'm using that will take in some text, it'll take in a string, and it'll return the embeddings, the vector embeddings I've created from my Azure OpenAI resource. So I'll go ahead and do that helper function. Whoops, it looks like I've already created this. But I can test to make sure everything's working correctly, right? So I can go and say, generate embeddings of the string that just says test. And here we go, I can see this vector embedding that's generated from my test data. And I think in this example, I'm using the Ada 2 model. In the other example, I'm using a different model, but this one I'm just using Ada 2. So now I just have a helper function that just shows how do I do a vector search in Cosmos DB, right? Cosmos DB features a really rich and powerful NoSQL query syntax. That's similar, but a little different to the SQL that we all know and love. And so here I can see that I'm just querying an item, and I'm using just a basic select clause, right? I'm saying select top, and maybe I'm going to say like select top 5, select top 10 results. And in this query, I want to project the title. So I'm looking at, I think this data set contains academic papers from archive.org. So I want to see the title of the paper. And then I'm going to use the vector distance function. So vector distance is the way that we do vector similarity search in Cosmos DB's NoSQL query syntax. So I'm going to project the vector similarity score here in my select statement. And then I'm going to do an order by vector distance. So this order by vector distance is what uses the vector index that we've already created using DiskANN. It's very powerful. So what I'm telling you is I want to order by in descending order, most similar to least similar results based on the vector similarity search. And I'll pass on some parameters as well, like how many results do I want back. And I've also parameterized the embedding that will call from the Azure OpenAI model. So we'll go ahead and run that helper function. And I've already run an example here. Maybe I'll clear all the outputs so we don't cheat. But here I'm going to run a vector search. I'm going to do it on 100,000 documents. And I'm going to use the DiskANN index. And I'm going to search for this phrase, supernovae and cosmic events. I'm going to generate embeddings from this. So it's going to create Azure OpenAI embeddings and use this in the vector search for Cosmos DB. And so I'm going to run this using the DiskANN algorithm. So let's run this and see what happens. So it runs and it finishes super fast, right? There's maybe a little bit of end-to-end latency because this resource is based in West Coast and I'm sitting here just outside of New York City. But we can see that the total execution time on the database itself was under 24 milliseconds, right? That's super fast. That's lightning fast. And we can see the results that we get here. I can see the similarity score, which I'm projecting. We saw that in the select statement. And I can see the title of the document as well. So I can verify that this seems right, that this seems what I was looking for. Now I can compare that speed to using the Q-flat, quantized flat index, right? So the quantized flat, again, it doesn't use this fancy graph-based structure. Basically, it does a brute force search on compressed vectors. So the trade-off is in very small scenarios, maybe under 10 or 20,000 or a few tens of thousands, it might actually be pretty good and I might want to use it. But for anything larger than that, I should really be using DiskANN and take advantage of its really powerful search capability. So what I'm going to do is I'll just comment out this vector search for DiskANN, and I'll uncomment the vector search for my quantized flat container. So these are the same documents, but they're just indexed in a different way using the quantized flat vector index in Cosmos DB. And so I'll clear the outputs and I'll run this. And cool, I can see that that was also really fast, right? It looked like a blink of an eye to me. but we can see that the total execution time in the back end was actually 59 milliseconds. And as I mentioned, like the tens of thousands of vectors or tens of thousands of documents, this is typically where you really want to evaluate, should I be using quantized flat or should I be using DiskANN? Because there are some cost or latency implications here. So if I was building an application out of this, with this 100,000 vectors, I would want to take advantage of DiskANN. It's very cost efficient, it's very fast, and I think it would be great for this application. So in our next example, we're actually going to do just that. So now that we saw how easy it is to use the Cosmos DB for NoSQL Python SDK and do vector search, we're going to go through our end-to-end chatbot. And again, I'm going to run through this, but I'll try to take some time and explain what's going on in every step. And you can follow along yourself. This is posted as a how-to guide in the Azure documentation for Azure Cosmos DB. It's also listed in a link, and the notebook itself is up on GitHub at the end of this. So when we present, when we go back to the slides at the end of this demo, you'll have a link to go get started there. So, all right, let's just go through it. Okay, so we're going to build this RAG chatbot with Azure Cosmos DB using Cosmos DB for NoSQL. We're going to use the Python SDK. We're going to use Azure OpenAI for our completions for our GPT model, as well as for our vector embeddings. And then we're going to implement RAG using vector search. We're going to implement a chat history stored in Cosmos DB, and we'll implement a semantic cache in Cosmos DB as well. And then we're going to tie it all together using Gradio. Right? Gradio is a really nice sort of front end, very customizable front end that you can configure right in Python, and it deploys a little web server so you can try out some AI applications very easily. It looks really nice, so I'm going to use it for our little sample here. Okay, so let's get started. So we install our required packages, we import all the libraries or packages that we need, and then similar in the other example, we load all of our connection strings, our database information, our OpenAI information, etc. The next thing that we'll want to do, and I've already done this ahead of time, so we don't use time in doing document insertions, etc. But the next thing that you would want to do is you would want to create a database in your Cosmos DB resource. Right? So in my Cosmos DB resource, I can create databases, and in every database, I can create containers or collections, or sometimes called, and that's where all my document data is stored. Those my data items are stored there. My vectors are stored as part of the data item. So we're going to go ahead and we'll create a database. And then before we create a container, we're going to define a couple of things that are necessary steps before we do vector search, right? We're going to create something called a vector embedding policy. And this vector embedding policy basically tells the Cosmos DB backend where to look in your documents for the vector embedding in your documents, right? So where are they stored? What property or path are they under? So what we do is we point it to a particular path of our JSON document. We tell it what data type we're going to use here. And so in Azure OpenAI, I think we're using text embedding 3 large vector embeddings here. So we're going to use float32 as our data type. OpenAI recommends using the cosine distance function for measuring vector similarity. So we're going to go ahead and use the cosine similarity function. And then you have to specify the number of dimensions, so the number of floats that are inside your vector embedding vector itself, right? And so we have this configured as a parameter, and Cosmos DB supports anything up to, I think, 4096 dimensions to your vector embedding. The Azure OpenAI models only go up to 3072, so lots of headroom there. So you can specify the dimensionality here. So once I specify my vector embedding policy that tells the database engine itself where to look for the vector embeddings in my data, next I define a vector indexing policy, right? So in Cosmos DB, I have to define I have to define indexing policies to effectively leverage the index when I'm doing queries for any sort of query operation. And vector search is no different, right? So I can define a vector property or a vector index in my indexing policy, and I do that here, right? So in this example, actually, I'm going to define this vector index. I think here I define a I'm using a quantized flat index. I think this example I have maybe 4,400 documents, 4,400 vectors. So I wanted to use quantized flat because it's good for those sort of small, very focused use cases. And all I do is I just need to tell it, hey, here's the property where my vectors are stored. And here's the type of vector index I want to use. I want to use a flat index, I want to use a quantized flat index, or I want to use a DiskANN index. So we use a quantized flat index here. And then I just create my containers, right? So I go through, so the chatbot that we're going to build here, I forgot to mention, is a movie chatbot. So what we're going to do is we're going to load a bunch of movie data into Azure Cosmos DB, and that data has already been vectorized. So we have title and descriptions of those movies that we've created vector embeddings from, and we're going to store all of that in Cosmos DB. And this data is available for you to use on GitHub. You don't have to worry about it. You can run this example end to end using the links that we talk about later. So, okay, created the vector embedding policy, tells Cosmos DB where to look for the vectors. Created my vector index, tells Cosmos DB how to effectively do vector search. And now I'm creating my containers that are going to store my data that I'm going to do RAG over. And I'll also create a cache container. So I'll create a separate container that'll store my chat history and my semantic cache data. So go ahead and do that. This has all been created ahead of time, so there's nothing really for me to do here. And then, just like we had previously, have some helper functions to call and generate embeddings from Azure OpenAI. And then, because this is an end-to-end tutorial in this Jupyter Notebook, you can actually get the movie data, vectorize it, and insert it into Cosmos DB yourself. And again, this takes a little bit of time because you have to vectorize, these 4,489 different documents. So again, I've done this ahead of time. I'm not going to waste time and sort of do this live for you. But you can go ahead and run this cell and do this exact sort of thing if you're running this on your own. Okay, so so now that I have my container set up, I have the data set up, there's some helper functions here for generating the vectors and inserting them into Cosmos DB very effectively. And again, you can go ahead and run that on your own. I'm going to skip this because I've already run it. And then you go ahead and insert all the data. Okay, so Cosmos DB setup, data is already there. Now let's get to the fun part, right? Just like we did in the other example, we create a vector search helper function where we execute a vector search query. And we return the results. So we can give this a test and make sure that it works. So here what I'm going to do is I'm going to search my movies data set in my movies container. I'm going to generate embeddings from the phrase Buzz Lightyear and Woody, and I'm going to return the top 5 results. And here what we can see is I have these documents that came up, right? Now in the search, I'm just projecting the overview or the description of the movie. So I'll see the descriptions of the movie here. I can see, led by Woody, Andy's toys live happily in his room until Andy's birthday. So great. Sounds like a Toy Story movie. And it sounds like there's a few Toy Story movies here, which is really great. So it seems like the vector similarity search is actually working pretty well. I'm finding my Toy Story movies, which I expected. Even this last movie here, right? This says star race car Lightning McQueen and his pal Mater head overseas to compete. And there's more detail here, but this movie actually isn't a Toy Story movie, right? This is actually from one of the Cars movies, right? But the vector embeddings themselves capture relationships between Buzz Lightyear and Woody and concepts that were found in this description of a Cars movie, right? It knows that it's a Pixar movie, it knows that it's an animated film, or it knows some characteristics about this. So these results turn up in the vector similarity search. So this is actually a really cool example of vector similarity search finding semantically similar items in our database to our search query, right? I didn't search for Cars movies or Lightning McQueen, but Buzz Lightyear and Woody, I guess, are close in vector space to the concepts that you'd find in the Cars movie. So pretty cool little thing that we just discovered here. All right, so we verified that our vector search is working. Now we have a helper function for getting chat history, right? So all we're going to do is retrieve from our chat container or cache container the last 3 items that were stored there, right? So the idea here is when I talk to a GPT model, or as I'm having a conversation with my chatbot, in addition to my current statement or my current text that I'm sending to the model, and in addition to any instructions that I'm sending the model, I also want to send some chat history. So that way it's aware of things that we talked about in the past, right? Or it's aware of something I referenced in my last sentence or last 2 sentences or 3 sentences, right? So all we're doing here is writing a helper function that writes a query that will find the last, n conversations that I've had with the large language model, and we'll send that to the large language model every time I talk to it, so that way it has context about what we talked about previously. Okay, so we have that helper function, and then we have our completion helper function. We have some system prompts, so instructions that we're going to send to a large language model. We have some a message queue here where we're loading up the system prompt, any chat history that we're going to get from our chat history stored in Cosmos, and then we'll also do a vector search here, right? So we'll find any relevant results from the user's question and send these back to the OpenAI model, right? So we're adding all of these things: the chat history, the user's question, the system prompt, and the results from vector search, and we'll add all of these together in a message, and we'll send this to our OpenAI model here using the completions API, and then we'll output whatever the model says back. So this is a nice little helper function for generating completions, and we have another helper function here that helps us sort of orchestrate these things. So for example, when I first have a message, before I send that message to the large language model, maybe I want to check my semantic cache to see if I've asked this question previously, right? So recall semantic cache just does a vector search on some of the previous data that you've seen in Cosmos DB, or previous conversations that you've seen. And you try to see, is there a relevant response in the large language model that I've seen previously, and then pull that up is something that I might want to dig into in Cosmos DB, right? We're going to implement this in our little Python function here, right? So we'll say check completion. We'll generate some embeddings from the user question. We'll check our semantic cache to see, has this question been asked before? And if it has been asked before, we'll say, cool, this was a cached result. I found a previous response, and we're just going to return that. If we haven't seen this question before, we haven't seen this prompt before, what we'll do is then we'll start our entire vector search pipeline, and we'll make a call to our large language model, right? So what we'll do is we'll do a vector search, we'll get the chat history, and then we'll send everything to our large language model, and we'll generate completion, and then we'll take that and we'll add that to our semantic cache, because maybe we want to call that up later. Then we'll just return everything that was returned. We'll return what the large language model generated in our case here. So again, this function just sort of orchestrates, do I want to do a semantic cache? And if there's nothing found, if I haven't found a similar question that was asked before, then I just execute my RAG and large language model pipeline for normal. Okay, so go ahead and run that. And then we have some helper functions here for generating your cached responses, right? So every time we're going to cache something in Cosmos DB, so every time we have a pair of a user's question and a response from our large language model, we're going to store that in our cache container collection in Cosmos DB. And so we're just defining some data to store along with it, right? So maybe we might want to capture a unique ID for this, right? We definitely want to capture the user prompt, or what the user asked. We definitely want to capture the completion, or what the large language model responded with when to this prompt. But we can also capture some other metrics that might be useful for analysis later on, like how many tokens did this take? How many tokens were used when the large language model generated its response? Or how many tokens went into the prompt that we created? Or what were the total number of tokens? Or what model was used? Or even what is the vector that describes my prompt, right? So lots of information here. And again, this example you can sort of study later on. But this is the sort of information that we're going to store in our semantic cache. That way, not only can we call this data for a chat history later on, but then we can do the semantic cache and vector search later to find frequently asked questions. So we'll go ahead and run that helper function. And then, okay, so that's a lot of setup. And again, I'm doing this all manually. You can actually do this in a lot of this in semantic kernel or LangChain, and it's much faster. And there are resources to get you started at link at the end of the demo here. But we did everything from scratch. And now we're going to create a really simple chatbot user interface using Gradio, and we're going to go ahead and run that. So here's my chat interface. Looks a little weird. in Visual Studio Code. So what I'm going to do is I'm going to click here, and I'm going to open it in a Edge browser, and I'm going to bring it over here so we can see it, right? So here we go. Here's our Cosmic Movie Assistant, right, for Cosmos DB. And we can ask it about movies in the Cosmic Movie database. So I'm going to say, tell me about movies with Buzz Lightyear. So what's happening here is it's checking semantic cache. Semantic cache is empty. We have never asked a question before. So it's going to take my text. It's going to generate a vector embedding of this text. It's going to execute a vector search in Cosmos DB, get the results back in lightning fast speed. And then it's going to send the results back along with our system prompts or instructions to our GPT-4o model that we've deployed in Azure. And then we can see the result from the chatbot. So I asked it, tell me about movies with Buzz Lightyear, and I can see the response. It tells me about these few stories, these few movies: Toy Story, Toy Story 2, and Toy Story 3. So awesome! Like, it found some of the movies that I wanted to find. These are definitely movies with Buzz Lightyear, so it seems to be working pretty well. And I can see, though, that it took about 4.2 seconds, so 4,200 and change milliseconds to execute. Most of the time here was spent actually waiting for my GPT-4o model to generate a response, right? We saw that the vector search in Cosmos DB is lightning fast, but the large language model is actually taking a bit of time to generate a completion for me. And this could be for various traffic reasons or the size of the payload that I sent to the model. But I can ask other questions as well, right? Like, tell me about Captain Kirk movies. Let's see what it says. Okay, so now it's going to do the same thing. It's going to take my search string, tell me about Captain Kirk movies, and it's going to do a vector search, find the relevant data, and send some of the chat history also to the large language model. And now I can see some movies, right? Star Trek II, The Wrath of Khan, the Star Trek movie in 2009, the reboot, Star Trek V, Star Trek Motion Pictures, Star Trek Generations. This is great. These are all Star Trek movies, so score it. And these are all Star Trek movies that have Captain Kirk in it. So that looks pretty good, like a pretty good response for my question. And I can do this all in this nice little interface here, right? So I can see an example of RAG working in this chatbot, which is really cool. Now let's see the semantic cache in action, right? So I'm going to ask the same question again. Tell me about movies with Buzz Lightyear. I'm going to ask the same question to the chatbot a little bit down here, and let's see what happens. I'll say, tell me about movies with Buzz Lightyear, and I'll hit enter. Okay, did you see how fast that was? Right, that was lightning fast. And what we can see here is I get the same response because I've asked the same question previously. And this time I'm able to do it in 412 milliseconds, right? Because doing a API call to Azure OpenAI to create vector embeddings is much, much faster than calling a GPT-4o model. And doing a vector search in Cosmos DB, we know is lightning fast. So all in all, like, the end-to-end time is 412 milliseconds for this. Really, really fast, like much, much faster. It's, 10x faster than what we saw when I didn't have a cached operation. And not only is it faster, but also I don't have to pay for the tokens, the input tokens for my GPT-4o model, or the output tokens. So I'm saving time and I'm saving money. It's the best of both worlds. So that about finishes up the demo here. So you can go and check this out as a guide. Again, there's documentation in the Azure documentation. There's a Jupyter notebook that I'll link to in a minute. And this can kind of help you get started on your RAG projects with Azure Cosmos DB and Azure OpenAI service. All right, so let me close or minimize out on what we were just talking about, and I'll bring back up my presentation slides. All right, so there's some links that are going to be available for you. I think they're going to be in the description, but there's also going to be links that you can just take from here. If you want to see a Jupyter notebook of this exact example, of this exact demo, you can check out aka.ms/cosmosdb rag with Python. It's case insensitive, you don't have to worry about it. But aka.ms/cosmosdb rag with Python will bring you directly to the Jupyter notebook that has this example. If you're looking for other documentation, demos, videos, link to some of our solution accelerators and other code samples, you can check out aka.ms/cosmosAI samples. This contains a huge library of documentation and samples and even videos like on YouTube that we've made that talk about vector search in Cosmos DB and in different applications. And then finally, if you want to just learn more and just have a good overview about vector search in Azure Cosmos DB, maybe you want to learn how to do it or how to set up the vector indexing policy, or you want to learn a little bit more about the flat, quantized flat, and DiskANN vector indices, you can go to aka.ms/Cosmos Vector Search and learn more there. Okay, one more thing before I go here. There's also something called Azure AI Advantage free offer. And so if you're a Azure AI customer, you can take advantage of this and you can earn up to $6,000 in free Azure Cosmos DB credits for 90 days. You can check out aka.ms/Azure AI Advantage blog for all the details. There are some restrictions, some caveats. You can go check it out and check out all the details there of how you can get up to $6,000 of free Azure Cosmos DB credits. So it's never been easier. It's never been cheaper to try to build your AI applications with Cosmos DB.
James, we do have a question from the audience.
Hey, great. Be happy to take it.
Yeah, absolutely. So Atir has asked, does Azure Cosmos DB allow for hybrid search with embedding and keyword search? If yes, then how?
Yeah, that's a great question. So today, Cosmos DB has system functions in our SQL syntax, in our NoSQL syntax. So you can do string matching, or you can do like clauses, or use regular expressions. So today, we don't have full text search. However, we are actually developing full text search, and we're going to be launching it in preview this fall. And you'll be able to do hybrid search in Cosmos DB. So you'll be able to take your vector similarity search and a full text search and combine the two to get even more relevant results. And so, again, we're going to be launching that later this fall. If I would encourage you to come to or watch online the Ignite 2024 conference, and you'll see some goodness that we're going to launch at Ignite.
Thanks, James.
All right. Any other questions?
I think we're looking good.
All right. Thanks all for tuning in. Thanks for spending the time with us. Again, if you have questions, you can feel free to reach out. There are some resources in the links that have been provided. But go try it out yourself. Let us know what you think. Let us know, is it awesome? Is it easy? Is it fun to use? Do you need a little bit more work? Are there features that you'd like to see? Let us know if you can help us shape the next version of Cosmos DB for AI applications.
Hey everyone, hope you enjoyed today's session.
If you aren't registered yet for RagHack, you can register now at aka.ms/raghack/register, and you can introduce yourself on our forum. You can start hacking either by looking at one of our code samples or just starting from scratch. If you have any questions along the way, feel free to post them in our GitHub discussion forum, and you can also attend live office hours in our Discord. Once your project is ready, make sure to submit it before September 16th at 11:59 p.m. PT to be eligible for our cash prizes. And of course, make sure to join our upcoming live streams to learn more about RAG. Thanks for joining.
Thanks everyone for joining. Thanks again to our speaker, James, for a wonderful session. To learn more about these series, watch past episodes, and sign up for future episodes, you can follow the link at the bottom of the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. You can find that link on the screen or in the chat. Today's event code is 23655.